Assalamu alaikum. Due to the current COVID-19 pandemic, all the JEE aspirants are stuck in their homes. I have started this online lecture series to help all those students. I hope that they will find it very useful. Stay home, stay safe. Assalamu alaikum. We are discussing the combination of the resistances. So let's start with a question. For example, we have a question like this. We have a triangle. Each side has a resistance of lambda ohm per meter. And we have to find the resistance between A and B. But within this triangle, there are actually infinite number of triangles and so on. So there are infinite number of triangles within this triangle, and we want to find the resistance between A and B. If the resistance of any, you can say, part of this triangle, the main triangle, it is lambda by 2. So since this point is dividing this line into 2, so the resistance of this part will be lambda by 2, and lambda by 2 multiplied by this distance. Let's say whatever be the length of this side. For example, this is 2 meters, so this will be lambda by 2 into 1, lambda by 2 into 1. If this is x meters, so this will be lambda by 2 into x, lambda by 2 into x, and likewise. But how to approach this problem? So it's very simple. Again, this is the same question that we have already solved, the repetition of the same pattern. But we have to see if the resistance between A and B is x, for example. If between A and B, the net value of resistance is x, for example. Now between these 2 points, for example, this is a point small a and small b. What will be the resistances between these 2 points? Now imagine a situation where we have all these triangles except the bigger one. For a moment, let's forget the bigger one. The inner one circle, it has again infinite number of triangles within it. But the only difference between this inner triangle and the main triangle is the length of the side of this inner triangle. It is half the length of this main triangle. So if the net resistance between A and B, for example, the net resistance of all these triangles, if that is x, the resistance between these 2 points A and B, excluding the main triangle, it will simply be between A and B, this will simply be x by 2. Why? It's very simple. Side length of this and the length of one of the sides of this triangle, the relation between these two is that this side is half the main, you can say, length of this main triangle. So this thing we can deduce. If AB has x value is the net resistance of this pattern, then between the A and B points, the value of the resistance will be x by 2. Now how to, you can say, approach this question? We can redraw it again. So we will draw it like this. This is A, this is B. So these 2 points, A and B, we will replace by x by 2. Fine. We will replace by x by 2. So this we can write lambda by 2, this is lambda by 2, this is lambda by 2, this is lambda by 2, and this is lambda. And we know that this is x by 2 only if the net value of the resistance between A and B is x. This condition. If we follow this condition, we reach to this. Now what will be the net resistance between A and B? That will be X. So I can write X equal to, so we have X by 2, that's they are in series. So this is, sorry, this is lambda by 2 and lambda by 2. So this is lambda parallel X by 2. So we will have a condition like this: A and B, one is lambda, second is, from this we have lambda by 2, this one. Then between these 2 points we have lambda by 2, it is lambda, and parallel with X by 2. So we have two things, X by 2 and lambda. Then we have lambda by 2, and we are reaching B. This is the pattern. Again we can say simplify it. So we will get to this point. We have A, we have B, one lambda is this directly, and then we have lambda by 2, that's lambda in series with these two parallel, means X by 2 parallel lambda. So I will write it like this: X by 2 into lambda divided by X by 2 plus lambda. So again these two are in series, so I can write plus, and this whole combination is in parallel with this lambda. So I get an equation. So I can write X equal to that combination. So lambda multiplied by lambda plus X by 2 lambda divided by X by 2 plus lambda divided by, because when we have two resistances in parallel, the net resistance is product divided by the sum. Simple. Or we can go by the formula 1 by R net equal to 1 by R1 plus 1 by R2. So but for two resistance, so we have one resistance lambda, and second resistance is the combination of these two. So this whole is parallel with this lambda. So I wrote here lambda multiplied by this thing, and then lambda plus this thing. Now this is again a quadratic equation. Simply we will get a power of, you can say, x raised to 2. So we can solve it and we can find the answer. So this is actually, I think this is in Irodov possibly, and this has been already asked in a couple of exams, maybe Olympiad I think. But such questions, you can say, this is a good way of understanding these patterns. So this is the way how we approach these questions. Simply identify the pattern that's repeating itself infinite times, whatever. So the first pattern we keep it like that. Rest of the pattern, that will be infinite minus 1, that we will, you can say, assign some value. That value should have some relation with the, you can say, the value of the net resistance of the circuit. So that we do like this. So the first point is identifying. The second point is, you can say, denoting the value, giving it some value, and then creating a kind of a relation between the first pattern and rest of the all the, you can say, patterns. So this is the relation there. Then redrawing the diagram and solving it. So this will help us, you can say, solving a lot of problems, but this is the way how we approach such problems. So every time you can pause the video. If you want to write anything, you can just pause it and note it down. Now let's start with the next part of this chapter, that is symmetry. So we have discussed circuits. They are asymmetrical, But if we have a symmetrical circuit, we can approach, you can say this, or get the solution in a very simpler way. For example, we have a problem like this. This is R, 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 and we have to find the resistance between point A and B. We have to find the resistance between A and B. Or we have a more, you can say, a bit complicated question like this. This one. How to solve it? So the simple approach is we will just try to get the net resistance by calculating or by just looking for some series and parallel combinations. But if we see these resistances here, this R is not in series with this R. The current is not same. We don't know. This R is not in series with this R. Now these two R's are neither in series nor in parallel. So what to do? Solve such problems. So now point number one, actually if we have an asymmetrical circuit with such a combination or such a pattern that resistances are neither in series nor in parallel, and we have such a combination, it is a bit difficult at this moment to solve this question. But later on you will see, if you can say in the first and second semester or third semester in the engineering, we discuss such circuits, and there is then transformation of del to star and star to del transformation that helps to solve, you can say, questions like this. But right now the symmetrical part, it is in the syllabus of the JEE, and we have to make sure we know this stuff. So we will be discussing only the symmetrical circuits right now. So this is a symmetrical circuit, and what do I mean by symmetry? For example, A and B, we have 2 points. So I will rub this part because this is the simpler one. We have A and B. We have to find the resistance between A and B. If we connect this with some, you can say, battery, the energy source, the current will flow. For example, the current is flowing from A to B. So what will happen? The current will flow from A, will get distributed through these, you can say, resistances in the circuit. Then after some, you can say, flowing through these resistances all, it will again get combined and exit the circuit through this point B. Now the spread of the current and the collection, or you can say again meeting at this point, or this point collecting the current from the circuit again, this spread and then again meeting at this point. In the symmetrical circuit, there are some simple, you can say, ways to deal with these, whether they are in series or in parallel. For example, when we say, for example, some current flows through this point A, it will spread. How does the current spread? The current sees different paths depending on the resistance source. So current is trying to find the least resistant path. The path with the least resistance, more current will flow through those paths. So from here, current will follow a kind of a pattern. Since this circuit is symmetrical, so the spread of the current and the collection of the current, they will follow the same pattern. For example, since these two are symmetrical, the current flowing through this R will be same flowing through this R. This is the common in between these two, you can say, the this part of the circuit and this part. So there will be some current. The current flowing through this R will again be same as current flowing through this R, because current sees very symmetrical paths. Whenever there is symmetry, current will equally, you can say, follow those paths without discriminating. So there is no way that more current will flow through this and less will flow through this. How we are doing this? We are simply looking at the symmetry of the circuit. We are not actually calculating anything, rather looking at the symmetry. Now we have to make sure that this symmetry is with respect to the A and B, these 2 points. For example, okay, we got it that there is a symmetry in the circuit. The same current will flow this. The current flowing through this will be same as this. The current flowing through this will be same as this. This is the common part. The current flowing through this will be this. So what can we do? Just what can we conclude from this? What we can do is, since the current flowing through this R is same current flowing through this R, we can disconnect this point like this. The moment we disconnect it, and this will not violate anything. Let's see, the current flowing through this R will be same as current flowing through this R. Now this we did on just looking into the symmetry of the circuit, not by solving it. Now it is very easy to solve this question. These R and R, they are in series, so it is 2R parallel with R, so 2 by 3R. Then these 2 R's are in series, and this is again in series, and these 2 are in series, and both are in parallel. So we can redraw it. R plus R is 2R, so we can say this is 2R. Then we can say this R are 2R parallel R, so we have 2 by 3R between A and B. Then we have this part, it is R and R, that is 2R. This is 2R, so this combination, and this we can again redraw 2R plus this. So we can say this is 2R parallel 2 by 3R 2R in series with 2 by 3R parallel with 2R. So that's the answer. So we employed something, we just discussed the symmetrical part, symmetry. We will again discuss the symmetry in a couple of more questions so that we understand it very much. So we will be discussing the symmetry. Actually, generally we have 2 types of symmetries that are actually needed right now. One is the folding symmetry, and the second is mirror symmetry. What is the folding symmetry and what is the mirror symmetry? We have to understand. For example, if we have to find the resistance between 2 points A and B, with respect to these 2 points, if the circuit is the mirror reflection, this part of the circuit is the mirror reflection of this part. So the left part is the mirror reflection of right part. For example, this is like this is like this. So these are mirror reflections of each other. We can have circuit like this, then like this, like this. So right part is the mirror, you can say, image of the left part. So this we are doing with respect to AB. And how to recognize it? Very simple. You just make sure you know where this A and B lies. Draw a perpendicular line in between the connecting line. That's any line connecting these 2 points. You just dissect this line with a perpendicular line. That is kind of a perpendicular bisector. So we draw this perpendicular bisector. So if the circuit happens to be symmetrical with respect to this line, so we will say this is the mirror image of this part. And whenever we have these mirror images, we disconnect this point. This is simple because of the symmetry. The current flowing through this will be same as current flowing through this. So this part of the circuit will not lose any current, and this part of the circuit will not gain any current. In case it loses, the current here will decrease. If this gains, the current here will increase. And if that happens, that will violate the basic law, because whenever we have symmetrical paths before the current, it will get distributed equally along all the paths. So current, you can say, does not discriminate. If current has two symmetrical paths, this will get distributed equally. So the simple point is first to determine whether we have mirror, you can say, symmetry or not. So this is the mirror symmetry. If we have mirror symmetry, disconnect that point. Simple, and we will get the answer. So let's try a couple of questions. For example, we have a question like this: how to solve it? So it's very difficult to solve this using, you can say, the conventional method. The simple way is A and B. Just by looking at this question, we have a feeling that this is the symmetrical circuit. And if we just divide this into two parts, so this is the center of this, and we will divide it into two. So this part is symmetrical with this part. The right part is symmetrical with the left part. When we have this kind of a symmetry, the perpendicular bisector, it is dividing this circuit into two parts, and both these parts are the mirror image of each other. So this is the mirror image of this. Simply what we will do, by symmetry, we come to know that the current flowing through this circuit will be same as current flowing through this circuit, because the current will spread equally along all the paths and will get collected equally. So we have these parts like this. If we divide it, so we have this part and this part, they are symmetrical. So means this current will be equal to this current. We have this spreading part and this is collecting part, they will be equal. We have this and this will be equal, and this will be equal. So what we will do, we will disconnect this point, connect it like this, and this question is solved. 2 plus 2, 4, 4 parallel 2, it is 4 by 3, then 2 plus 2 is 4, 4 plus 4 by 3, 16 by 3, and then we have parallel 2 and 2, 4. So 16 by 3, parallel 4. Then we have these two, they are in series. It's very simple. Second symmetry, we will discuss the folding symmetry. If we have 2 points, and with respect to those 2 points, we can fold the circuit. How we do it? Let's see. For example, we have a circuit like this. This is A and this is B. And this is R, this is R, this is R, 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 and likewise R, 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 R. For example, this is the case. Now this looks very, you can say, messy, and it's very difficult to solve this problem. Now see, is it possible for us to get a kind of a mirror symmetry in this. At times what happens, we have both symmetries in a circuit. We have the mirror symmetry as well as the folding symmetry. But right now we will use the folding symmetry. What does that mean? So that means this circuit A and B, we have a circuit. The current will flow through different, you can say, parts of the circuit. Now see, if the potential at this point is maybe A and the potential point at this is B, we know since the circuit is symmetrical, the potential at these 2 points will be same. This is very important to understand. Why? Actually, if we see the paths, these 2 points are equidistant from A. The current flow through both will be the same. If the current flow through this I, the same will be through I, because this is a symmetrical circuit. The upper part of the circuit and the lower part, these 2 parts are symmetrical. Since they are symmetrical, the current flow through this will be same as this. And the conclusion of that is, if the potential at this point is maybe A, the potential at this point will be A minus IR, this point. And the potential at this point will be again A minus IR, because the I through this and I through this resistance, they are the same. If potential here is A, the potential here will be A minus drop, that is A minus IR. The potential here will be A minus IR, again same. So it means the potential at this is A and potential at this and this point, potentials are same. They are same. Since the potentials are same, we can say these 2 resistances are in parallel. Likewise, these 2 resistances will be in parallel, these 2 resistance will be in parallel, these 2 resistance will be in parallel, and these 2 will be parallel. So it is like we are dividing the circuit into 2 parts, like cutting it into these 2 parts, and we are folding this part over this. So what we are actually doing, we are doing like this. We are folding this on, based on this calculation. So when we fold this part over here, what will happen? This R and this R, they will be in parallel. So I can redraw it. So the R, this R will remain like this R, and then this R, this is B. When I fold this over this, what will happen? This and this will be in parallel. So I will have, this will be R parallel R, R parallel R. So this point we reached. Now this will be parallel with this. So I will get R parallel R. Then I have these 2. So I will have R parallel R. Now we have these 2, R parallel R, and these 2, R parallel R. So R parallel R means R by 2. This is again R by 2. This is R by 2. This is R by 2. So this is R, 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 R. So actually the answer will be simply this. We can ignore right now for the moment, but later on we will see in the Wheatstone bridge how to calculate this answer. But right now, if we ignore it, let's ignore it right now. Or we can use again the symmetry. So if we ignore this, the answer will be R parallel R, R parallel R. So the answer will be R. So answer of this question is simply R. And what we did, we cut it into 2, you can say, parts. But right now we did cut it along the axis of this, you can say, axis of the line joining these 2 points A and B. Before this, in the mirrored symmetry, we did cut the circuit into 2 parts along the perpendicular bisector. So that we called as a mirror symmetry. But right now we are folding it. So we call it the folding symmetry. And what happens in the folding symmetry? The potentials, you can say, at different points, they are symmetrical. Since the potentials are symmetrical, we get a kind of, can say, we easily replace these 2 parts and we merge it into one. तो इन दोनों को हम पैरेलल यहाँ बना सकते हैं. So this is how we use the folding symmetry, and this is known as folding symmetry. So these two symmetries, the mirror symmetry and the folding symmetry, they help us to solve the problems like this. We will again discuss a couple of questions. For example, we have a question like this. So how to solve it? For example, the value of this is 1 ohm and all these resistances are 1 ohm. So looking at this image, we have a feeling, we get a feeling like this is a symmetrical image. So we can have two types of, you can say, symmetries, but let's see whether we can say we can go for the folding symmetry or the mirror symmetry. For example, we have 2 points. हम इसके परपेंडिकुलर बाइसेक्टर लेंगे यहाँ से, we take a perpendicular bisector. ठीक है, यहाँ से परपेंडिकुलर बाइसेक्टर मेरा हो गया. अब मैं देखूं क्या ये इस सर्किट को दो मिरर इमेज में काट रहा है, नहीं काट रहा है. So this part of the circuit and this part of the circuit, are these two parts mirror image of each other? Yes. If we see to it, yes, they are mirror image. हो सकता है. अब हम फोल्डिंग भी ट्राई करते हैं. क्या फोल्डिंग है? फोल्डिंग में सिंपली हम ए और बी के बीच में एक्सिस लेते हैं. सो दिस इज द एक्सिस. क्या ऊपर वाला इस एक्सिस के ऊपर वाला और इस एक्सिस के नीचे वाला, यानी कि ये वाला एक्सिस, इसके ऊपर वाला ये वाला पार्ट, इसके नीचे वाला ये वाला, क्या ये आपस में मिरर इमेज है? यस. तो इस वाले क्वेश्चन में हम फोल्डिंग सिमेट्री भी यूज कर सकते हैं. इस क्वेश्चन में हम मिरर सिमेट्री भी यूज कर सकते हैं. अगर हम मिरर सिमेट्री यूज करेंगे तो सिंपली इसमें से करंट इसके बराबर होगी, तो इस पॉइंट को हम डिस्कनेक्ट कर लेंगे. सो वी विल रीड्रॉ इट लाइक दिस. इन तीनों को डिस्कनेक्ट करके लाइक दिस, और हमारा जो भी क्वेश्चन है सॉल्व हो जाएगा इजीली. 1 and 1 is 2, 2 and 1 is 2/3, 1 and 1 is 2, 2 पैरेलल 2/3, और ये दो सीरीज हो जाएगा हमारा सॉल्व. बाकी इजीली हो जाएगा अगर हम मिरर सिमेट्री लें. अब अगर मिरर सिमेट्री ना लें और हम यूज करना चाहें फोल्डिंग सिमेट्री, क्योंकि इस क्वेश्चन में दोनों यूज हो सकते हैं, क्योंकि ये सिमेट्रिकल अलोंग दिस परपेंडिकुलर बाइसेक्टर भी है और अलोंग दिस एक्सिस कनेक्टिंग दिस पॉइंट्स ए एंड बी. दोनों लाइंस के विद रेस्पेक्ट में ये सिमेट्रिकल है. तो अगर हम पैरेलल लेंगे तो हम ऊपर वाले को पूरा काट के इसके ऊपर डाल रहे हैं, तो इसकी वैल्यू हम इसको रब करके सिर्फ ये लिखेंगे, और इसमें वैल्यू क्या लिखेंगे? देखिए ये इस पे आ जाएगा, तो 1/2 पैरेलल, 1 और 1 पैरेलल में 1/2. सो दिस पैरेलल विद दिस, ये 1/2, ये भी 1/2, 1/2, 1/2, 1/2, 1/2. ये वाला 1 रहेगा, ये वाला 1 रहेगा. ऊपर वाला हम रब कर सकते हैं, ऊपर वाला पार्ट हम रब कर सकते हैं, क्योंकि उसको हमने फोल्ड कर दिया हमने. अब जब हमारे पास ये आ गया, अभी भी अब ये सॉल्व नहीं होगा. क्यों? क्योंकि अभी भी यहां पर एक पॉइंट कनेक्टेड है इसके साथ. तो हमें फिर से इसको क्या करना पड़ेगा, देखेंगे आप. अब हमें फिर से इसको सॉल्व करने के लिए मिरर सिमेट्री यूज करनी पड़ेगी, क्योंकि मिरर सिमेट्रिकली बीच में मिरर सिमेट्रिक है ये, इसलिए हम ये वाला पॉइंट डिस्कनेक्ट कर सकते हैं. वी डिस्कनेक्टेड लाइक दिस, और अब ये सॉल्व हो गया. सो वी हैव टू वेज. या तो हम पहले फोल्डिंग सिमेट्री फिर मिरर सिमेट्री लगाएं, या सिर्फ मिरर सिमेट्री लगाएं, फिर तो आराम से क्वेश्चन हो जाता है. तो ऑब्वियसली अगर हम एग्जाम में इसको करेंगे तो हम सिर्फ मिरर सिमेट्री यूज करेंगे. 2 बार हमें सिमेट्री यूज करने की जरूरत है नहीं। तो ऐसे भी क्वेश्चन आ सकते हैं और ऐसे भी हम इसको कर सकते हैं। हमारे पास और एक तरह का क्वेश्चन है, जैसे कि आप ये देखेंगे, जैसे ये वाला क्वेश्चन। इसमें कौन सी सिमेट्री हम लगा सकते हैं? लगा सकते हैं, नहीं लगा सकते? और क्या ये सिमेट्रिकल है, नहीं है? ये हम इजीली कर सकते हैं। तो ये हम एज असाइनमेंट आप खुद करेंगे। इसमें क्या कर सकते हैं, इससे भी और एक चीज, इसको थोड़ा कॉम्प्लिकेट करके, ये वाला क्वेश्चन, इसमें कौन सी सिमेट्री यूज करें? इस क्वेश्चन में एक कंफ्यूजन हो सकता है बच्चों को। फॉर एग्जांपल, ए और बी को भूल जाओ एक मिनट, ये वाला पैटर्न देखो। तो अगर मैं इसको यहां से डिवाइड कर रहा हूं तो मेरा मिरर बन रहा है, और अगर मैं इसको ऐसे डिवाइड करता हूं तो मेरा फोल्डिंग बन रहा है। तो कुछ स्टूडेंट्स क्या कर रहे हैं, few students, what they do, they try to analyze the circuit in this way, and they get a notion that we can use the mirrored symmetry, that's obvious, and we can also use the folding symmetry. But we have to understand, we always analyze this folding and mirror symmetries with respect to the specific axes. So when we are talking about the mirrored symmetry, we have to draw a perpendicular bisector. Fine. For example, if we draw it and we see there's a pattern, it's fine. But as far as the folding symmetry is concerned, this figure, this circuit is symmetrical with respect to this axis, but our folding, you can say, symmetry is always with respect to the axis connecting these 2 points, A and B, because we already discussed this folding symmetry is nothing but we are deducing it from the symmetry that these different points are at the same potential with respect to some main, you can say, the axis of this circuit, or we can say this point. इस point के respect में कुछ points हमारे same potentials पर है, इसलिए हमने कहा कि वो दो जो components हैं वो parallel में होंगे। तो यहाँ पर इसके इस वाले एक्सिस के रेस्पेक्ट में तो फोल्डिंग सिमेट्री हो सकती है, लेकिन ये तो हमारा कभी मतलब ये तो मेन एक्सिस हमारा है ही नहीं। मेन एक्सिस हमेशा वो होता है जो दो रेजिस्टेंस जिनके बीच में हमें रेजिस्टेंस निकालना है उसका जो एक्सिस होता है, तो ये वाला हमारा मेन एक्सिस है। और हम देख रहे हैं इस एक्सिस के रेस्पेक्ट में दो साइड तो है ही नहीं, यहाँ तो एक ही साइड है, तो इसमें हम फोल्डिंग नहीं लगाएंगे लेकिन मिरर लगाएंगे, और जैसे ही मिरर लगाएंगे मिरर सिमेट्री, तो ये वाले पॉइंट्स डिस्कनेक्ट होंगे लाइक दिस, और हमारा आंसर आ जाएगा। तो आंसर अब सिंपल है, R and R 2R, R and R 2R, 2R 2R parallel means R, R, R and R means 3R. Likewise here, these 2 R's and these 2 R's, so this is R, 2R and 3R, so 2 by 3R answer. So what we conclude from this is we have some complex circuits at times which we cannot solve by the conventional methods. So we have to see, we have to look for the symmetries. We have two types of symmetries. We have the folding symmetry and we have the mirror symmetry. These two symmetries help us in analyzing and solving this circuit, or finding the net resistance between the 2 points. This is very important topic as far as the JEE is concerned. So with this we finish a part of, you can say, the combination of the resistances. This part is over. Now we will jump over to the next part, that is finding the resistance between 2 points when the circuit is in the 3-dimensional circuits. Plus we will try to analyze the circuits, few complex circuits where it is very difficult to find the answer using the conventional methods, then using these symmetries when it is very difficult to find the answer using these two methods. Then we deploy some other method and we will discuss those things. Thank you very much. See you in the next lecture.